Hello and welcome to another video on C-star algebras from a novice perspective. Today we're going to talk about approximate units. And these can be very useful in proofs when the existence of a unit element is not assumed, and since they can sometimes work as sort of a stand-in for such an element. But before we get to the approximate units, let's repeat what we did the last time. So we talked about positive elements, and these are self-adjoint elements whose spectrum is a subset of the positive real line. And we saw that the positive elements determine an order on the self-adjoint elements of A by setting A is less than or equal to B if B minus A is a positive element. And finally, we used the power of continuous functional calculus to prove a number of familiar properties for positive elements. For instance, we showed that every positive element has a unique positive square root. We proved that the sum of positive elements is a positive element, and that any element of the form A star times A is positive. Now, the fact is that if we use this fact that every positive element has a unique positive square root, we see that, in fact, the set of positive elements in a C-star algebra is actually the set of elements that can be written in this way, as the product of A star times A for some A in the C-star algebra. And this is something we're going to use repeatedly when we work with positive elements, this sort of characteristic property of them. But before we can talk about approximate units, which will be the main focus of this video, we need to talk a bit about nets, because approximate units are defined using nets. So what is a net? Well, it's the replacement for the notion of sequence. So if we have a net in a space X, then it's a function from some index set lambda here to the space X, which we can call the underlying space or whatever. And this set lambda, if we think of sequences, then lambda would be just the set of natural numbers or the positive integers. But in this case of nets, we want to be a bit more liberal with what lambda can be. And we say that lambda should be a directed set. What does this actually mean, though? Well, it means that lambda, first off, should be a non-empty set, and it should have a preorder, which we denote by this less than or equal to sign again. And this preorder should be such that for any pair of elements, lambda and lambda prime, inside of the index set, then there should be an element mu in the index set such that lambda is less than or equal to mu and lambda prime is less than or equal to mu. That is, mu should be a common upper bound for lambda and lambda prime. And this is actually equivalent to stating that every finite subset of this index set lambda has an upper bound inside of lambda. And you might think that it's kind of strange to have two elements to have a common upper bound. Why not just have one? For every element there is an upper bound. But really, this is what we do to have this statement here, that every finite subset of lambda has an upper bound in lambda. So these two are equivalent. I won't go into details as to why that is. I just want to note that these two conditions for directed sets really mean the same thing. And nets generalize the notion of sequences in a very clear way, since if we take this, lambda equal to the set of natural numbers, we get a sequence. And this is indeed a directed set, just using the natural order that we have on numbers. Now, a more interesting example for us is the net, which is just the non-negative integer or the non-negative numbers of the real line that are less than 1. And we can have this net be anywhere. We can have it on the real line, but we can also have it in the complex plane, which might be more interesting for us since we're studying C-star algebras. And indeed, we can see that this is a net by letting lambda be equal to that set itself, and then just taking this function f that we have here to take lambda to lambda. That is, it's the identity function. And now the pre-order on this set lambda that we have is of course the usual order that we use on the set of real numbers. And one might be a bit confused about nets to begin with as to why someone would ever bother using them. And the fact is that when you have a general space X here, topologically speaking, it can have some sort of pathological properties that are not very nice. And normally you would like sequences to be able to encode information about continuous functions between topological spaces. But this is not possible for sequences to sufficiently do if the spaces are not first countable. Now, I won't go into detail as to what a first countable set is. That's topology, that's for a completely different video. But if you're interested, you know what the condition is at least. And you can look it up anywhere. Now, when we have nets, we can define approximate units in the following way. So an approximate identity, and now you will see me conflate identity and unit all over the place. Just deal with it. I hope it's not too bad, but just see that I will use approximate unit or approximate identity here and there all over the place. So an approximate identity for a Banach algebra A is a net, which we denote in this way, for lambda in this sum directed set, or the index set, which is a bounded net. And since we have a Banach algebra, of course we can have bounded nets. And this net should satisfy the following limits. So the limit of e sub lambda times a should be the limit of a times e sub lambda should be equal to a for every a in the C-star algebra. And just a quick note, how do we even take limits in a net? Well, it simply means that we do like we do for sequences. We go up and up and up and up. So first we'll look at a1, then or e1 or e2, e3 and so on up till to infinity. And we really do the same thing here because we have this pre-order and we have a directed set. We can always find an upper bound, bigger, 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 bigger. And that is basically what we mean by this limit here, that no matter how high we go in this directed set, we should get closer and closer to whatever limit we have. So the reason why we use nets instead of sequences in this definition is because, well, Banach algebras can be pretty ill-behaved topologically speaking. Now, if your Banach algebra that you're working with is well-behaved enough, then you can probably use sequences instead of nets without any sort of loss of generality, or you basically won't lose anything if the algebra is well behaved. But if it's pathological in some essential way, then maybe it's better to stick with nets, even if they might be a bit more confusing to deal with. Now, a simple example of an approximate unit is in fact the net that we talked about in the previous slide. That is the non-negative real numbers that are less than 1. And this is of course an approximate unit in the C-star algebra of complex numbers. Now, our main goal today is to prove that an analogous approximate unit exists for any C-star algebra. So this particular example I gave was not really that much just an easy example. It's also a very important approximate unit in C-star algebras. And we shall see that every C-star algebra has an analogous approximate unit or approximate identity. So, how do we actually prove this? Well, first we need to find the right net, and we're going to see that it's the following net or directed set. That we have lambda here be the index set, which is all positive elements in the C-star algebra with norm less than 1. And this is really what we're looking for. And to prove that this is an approximate unit, we need to complete 2 steps basically. First off, we need to show that lambda, together with the order that we have, given by this positivity condition, we should show that it's a directed set, meaning that we can think of lambda as an actual net. And we're going to do this by using continuous functional calculus. I mean, why wouldn't we? And then, once we have that lambda is a net, we need to prove that it's actually an approximate unit. Of course, it is bounded, but how do we prove that these limits hold? Well, here we actually use a very common proof strategy when you deal with nets, and that is to consider an appropriate so-called cofinal subset of lambda. And here the term cofinal subset should be thought of as sort of the equivalent of a subsequence for sequences. But before we can really get into proving this main thing, that is, first we prove that lambda is a directed set, and then we can prove that the limits are what they are supposed to be, we need a useful lemma first. And that is something that should be quite expected for positive elements. That is, if A and B are positive elements, such that A is less than B and both A and B are invertible in the algebra A, then B inverse is less than or equal to A inverse. And this is a proof that is basically just calculation, as you can see. And the first step is an exercise for you, the viewer. And that is that if you have two self-adjoint elements x and y here, such that x is less than or equal to y, then I'd like you to prove that for any z in the C-star algebra A, we have that z star times x times z is less than or equal to z star times y times z. This might look difficult, but if you use positive elements and their basic properties and the fact that they have unique square roots, you might get out of this without too much hassle. Now, using this fact that I hope you've proven out by now, combined with the fact that b minus a is a positive element in our assumption here, then we have that 1 minus the square root of b inverse times a times the square root of b inverse is of course equal to this expression here, b inverse times b minus a times b inverse, or the square root of b inverse here. And by this statement here, that you've proven by now, I hope, we have that this is of course greater than or equal to 0 because b minus a is greater than or equal to 0. And thus we see that this expression here, which can be rewritten in this way here, is less than or equal to 1, which implies that the norm of square root of a times the square root of b inverse is less than or equal to 1. And hence, we can use this fact to get the following. So we take just and calculate the other way around. So first we looked at square root of a times square root of b inverse star times square root of a times square root of b inverse. But now we look at it in the other direction. So we look at the square root of a times the square root of b inverse times the square root of a times the square root of b inverse star. So look here, the star is the difference in which order we multiply these two. But we see that they of course have the same norm. And this expression here is just equal to square root of a times b inverse times square root of a. And now we're going to use this inequality here once again in a clever way by multiplying by both sides of square root of a inverse to get that a inverse here is of course equal to square root of a inverse times the unit times the square root of a inverse, lots of words there to say. And we can just use this inequality that we have that 1 is of course greater than this expression here. Or maybe I should use rather this expression here. So we have this inequality here. So we have that this is greater than or equal to this. But this is just something we can calculate explicitly, and it's just b inverse. So we have proven the statement that seems very obvious, that if a is less than or equal to b, then b inverse is less than or equal to a. And now we're ready to prove that this set lambda is actually a net, or that it's a directed set, whichever way we'd like to state it. So we need to use functional calculus in some way. So what functions are we going to use? Well, first off, we're going to use f of t equal to t times 1 over 1 minus t for t greater than or equal to 0 but less than 1. And we'll let g of t be t times 1 over 1 plus t, which can be rewritten as 1 minus the inverse of 1 plus t for every t greater than or equal to 0. Now, we note that g of f of t is just equal to t. That is, it's the identity function. And you're welcome to pause and verify this. In fact, I encourage you to do so. But I'm just going to skip past and assume that you have checked this. Now, look at this here. F of t is, of course, a well-defined function for elements in this set lambda here. So suppose that a and b are in lambda and set y equal to f of a plus f of b. Now, you may wonder, why are we doing this? Well, remember what the definition of a directed set is. That is that we should have, for every a and b in lambda, we should try to find another element that is a common upper bound for both of them. So we do this by first setting y equal to f of a plus f of b. And then we take c to be g of y. So now we don't really have much control over y here or anything. Y doesn't have to lie in the set lambda, but c actually does. And this is because if you look at the expression g here, or the function expression for g here, then you see that no matter what value you put in here, so no matter what the spectrum of y can be, the absolute value of g can never even be 1. It always has to be less than 1. And since the norm of g, or c, is equal to basically the absolute norm of g here, then we see that c must have norm less than 1. And it's of course also by functional calculus going to be a positive element. Now, one little detail that I would like to note before we move on is that all of these expressions, f of a, f of b, g of y, and all of this, these all lie in the C-star algebra A that we began with. And that has to do with f of 0 equal to g of 0 equal to 0. And this is just functional calculus. You can watch that video or the Gelfand transform to really see what I mean by that. But this is actually quite an important detail, because once again, we're dealing with approximate units, and we might not even have a unit in our C-star algebra to begin with. Now, once again, the thing we need to prove now is that this C that we just constructed is the common upper bound for us. And for this, we actually do need a unit in our algebra. Now, if A is a non-unital algebra, we consider the unitization of A. But we still remember that all of these expressions that we have here, they still lie in the original algebra. We don't need to involve the unit to get these elements. So, now that we have a unit, we can set x equal to f of a. Now, of course, f of a is less than or equal to y, because of how y is constructed. And this implies that 1 plus x is less than 1 plus y. And now I leave it to the viewer to figure out why these are invertible elements. But they are invertible. There is no issue whatsoever here. Because, well, I'm not going to spoil anything. Have a blast trying to prove that these are invertible. But since they are invertible, we can use the previous lemma to state that the inverse of 1 plus x is greater than or equal to the inverse of 1 plus y. And thus we have that a, which is of course g of f of a, because g of f of t is t, the identity function, so really a is g of f of a. But g of f of a is of course g of x here. And g of x corresponds to this function here, but it's just this function right here. And this expression is of course less than or equal to this expression because x is less than 1, and this inverse of 1 plus x is greater than or equal to the inverse of 1 plus y. And then when we have this expression here, then by the same reasoning as for x, this is just g of y, but that is defined to be c. So we see that a is less than or equal to c. C is an upper bound for a. And of course, similarly, b is less than or equal to c. And this implies that lambda, by definition, is a directed set in A, meaning that we can consider it to be a net by just mapping every element in lambda to itself, which of course lies in A. And now that we have that lambda is a net, we can go on to prove that it's actually an approximate unit. So we need to prove that these limits that we have really tend to 0 here. So x minus lambda x, it should tend to 0, of course, and x minus x times lambda should tend to 0 as lambda increases in the directed set for any element x in the C-star algebra. Now, if a is less than b, and both of them lie in lambda here, so they're positive, and if x is an a, then we have the following. That the norm of x minus bx squared can be rewritten as this expression here. And once again, if we don't have a unit in our algebra, then we're using the unitization, but no problem is going to arise because of that. And this expression here, we can use the Banach property of the norm to show that this is of course less than or equal to this norm here, and that has to do with the fact that the norm of 1 minus b is less than or equal to 1. But here we have that 1 minus b is of course less than or equal to 1 minus a, so x star times 1 minus b times x is of course less than or equal to x star times 1 minus a times x. So the norm, this norm, is of course less than or equal to this norm here. So a long way to prove that the norm of x minus bx squared is less than or equal to the norm of x star times 1 minus a times x. And similarly, we can prove that the norm of x minus xb squared is less than or equal to the norm of x times 1 minus a times x star. So basically just the conjugate there. Or maybe not the conjugate, but we flip all the factors. Now, we have proven basically what amounts to a lemma here. So we haven't really gotten to proving this limit up here yet, but now we're going to get to it. And we do this by finding this, I call it the cofinal set, but we can really think of it as a suitable subsequence or subnet of our net lambda that is going to give us this limit that we're after. And as in the last slide, we use this function g of t once again, which we defined to be this, which is equal to 1 minus 1 plus t inverse for t greater than or equal to 0. Because as we saw in the last slide, we have that g of x is always in lambda for any positive x here. And if we look at any x greater than or equal to 0, then we set a sub n equal to g times n, or g of n times x, which is of course still in the set lambda. And then we set h sub n of t equal to this expression here, t squared times 1 minus g of nt, or 1 minus an you could say here, or something. We're going to see how things work out. And this of course is equal to this expression here if you actually write it out using the definition of g. And if you just use simple estimations, you see that this is of course less than or equal to t divided by n. And from this, we see that if we look at the norm of x times 1 minus an times x, then this is actually equal to the norm of h of n, hn of x. And this has to do with an here, as it's defined. It actually commutes with x, because remember, we define all of these expressions by going into the commutative algebra generated by x. So we have that a sub n here, it actually commutes with x, so we have that this expression here is really equal to this expression here. And this is less than or equal to this norm here, and this is just the supremum norm on the spectrum of x. And the supremum of h of n, well, it can never be greater than this value here. And here's the whole point of doing all of these constructions. We have that these lie in our directed set lambda, and we also have that these terms here, they tend to 0 as n increases. So now we have that the limit as of this expression here, x minus lambda x, and if we look at that norm squared, this is of course less than or equal to the limit as n tends to infinity of the supremum of all lambda greater than or equal to a sub n here. So this is really the trick we're using. We're using this cofinal set that is generated by these an to pick out what we're after, because this expression is something we can actually estimate. Because if we look at the previous slide real quick here, we see that this is exactly what we proved up here, that we can actually get that this left hand side is less than or equal to this right hand side here, and likewise if we switch the order of multiplication, nothing happens. So we really get down here that the supremum, if lambda is greater than or equal to a sub n of this norm here, is just less than or equal to this expression here. So of course this limit is less than or equal to this limit here. But we also know by this estimation here that this limit must be 0. And similarly, the limit, if we, instead of looking at lambda times x, we take a look at x times lambda, we get similarly that this limit is also 0. So of course this limit of the norm squared is equal to 0, of course implies that the norm without the square also tends to 0. So we see that the limit, these limits that we're after, are in fact the correct limits if x is a positive element. But how about general x? So here we are always assumed that x is actually positive. And I'm actually going to leave it to the viewer to use all of the above results to finish this proof. That is to show that these two limits hold right here. And I hope that you can prove it without too much difficulty. Now, I would say this, that as a hint, do not just consider these norms as they are. Don't just try to write these limits of these norms explicitly. Try to calculate the limit of the square of the norm like I did up here. And when you do that, you can use the C-star property to your advantage. So I hope that's enough as a hint, but if you're struggling to really finish off the proof, then just write in the comments and I can give some more steadfast direction. But let's go over to the recap for now. So first off, in this video we talked about approximate units, which are bounded nets that can be used instead of units to prove some general statements about C-star algebras. And every C-star algebra has an approximate unit given by this particular directed set that we have here. And I would just like to end by saying that this is of course not necessarily the only approximate unit in a C-star algebra. In fact, there can be many such approximate units, but this one that we have here always exists, and that's the important part of this video, that no matter which C-star algebra you're looking at, it is always going to contain an approximate unit, which is great when you want to prove stuff, because they can, as I said, even in the case of non-unital C-star algebras, you can sometimes get away with using the approximate units instead to prove statements that seemingly need a unit to work. So that's it for now. Hope you enjoyed this video, and if there's anything weird about it, or if you have any questions, just write in the comments below and I'll try to answer them as quickly as I can get to them. Thanks for watching, and goodbye.